All right, guys, this is the last question I wanted to get to in class, and we just couldn't quite make it. And you know, that's all right. But I am going to go through it now because I feel like our homework tonight will be much more productive if you've had time to look at a question that has a pulley. Okay, so that's what this guy is here. This is a pulley. It's fixed in the middle. It spins just like most things in this physics class. We're going to assume that that pulley is frictionless. Okay, massless. It's not going to be affected. Later in this course, we're going to talk about rotational kinetic energy. We're going to assume that it's massless, so it doesn't have any rotational kinetic energy. Yeah, maybe or maybe not a great assumption, but that's what we're going to do so that we can get the ideas here and understand and be able to really put ideas together. All right, so we've got a big mass, we've got a little mass. What we're going to do here is we're going to attempt to write a formula for the acceleration and a formula for t that only has these constants, big M for the big mass, little m for the little mass, and also g, because g is a constant, a fundamental constant that we're comfortable with. So we're allowed to have that in our answer as well. The only other thing I'm going to mention is that we are going to assume again that this is smooth. We don't want to have to deal with friction yet. We'll get there next class. I promise. We'll be there. But yeah, we're going to assume smooth, no friction. All right. Now, when dealing with a pulley, okay, there are a couple of things that are going to be helpful. One is to deal with the system. Just like we talked about in that previous question, if we deal with the system, things may be a little bit easier. It may simplify things for us. Okay. The other thing is that with pulleys, the vertical and horizontal are going to make things difficult, right? Because the vertical on this guy, that vertical isn't going to affect my system, right? At least not if there's no friction. The vertical here is going to be balanced most likely by the vertical of the table, right? However, the vertical here will cause acceleration. And so what we're going to do is we're going to instead of looking at horizontal and vertical, this is very similar to the ramp. Remember when we had the ramp, we changed things slightly. We said, you know what, our x-axis is going to be slanted like this, and our y-axis is going to be perpendicular to the surface. This is kind of a convention like that, is we're going to allow anything that causes the pulley to go one way to be positive, and anything that would make the pulley turn the other way to be negative. All right, so let me demonstrate. In this case, I know that because of the mass here, it's probably going to drop. So I'm going to define that as positive because I like positive. Positive numbers make me happy. It just makes it easier to work with. So I'm going to say positive is anything that causes my pulley to rotate in this direction, clockwise, right? I could have just as easily defined positive being the other direction. And in fact, when we get to rotational dynamics and things like that, we often just straight up say counterclockwise is positive. Done, always. Okay, but in a system like this, it really doesn't matter. Okay, we are going to just say, you know what, I'm going to make this positive. In fact, there are some textbooks that always say that clockwise is positive. It really doesn't matter. Okay, so I'm going to define this as positive. So now I'm going to do my forces, okay? But I am going to treat it as a system, okay? Because I don't necessarily need tension right away. I can probably get the acceleration without it. So I'm going to do a system on this block, and my system is this, okay? Not including the pulley there. This is my system. All right, so anything that goes this way is going to be positive. Anything that goes that way is negative. So we think about what are the forces on my system here, right? Well, it depends because different pieces have different related forces, right? We do have an overall force of gravity downwards, okay? But I'm going to do those pieces individually here, right? So I'm going to take the forces that are over here. I've got the force of gravity on M, and then I've got the normal force on the capital M. Okay, those two forces are on my system. Okay, I also over here, I've got tension, but that is inside my system, so I don't have to worry about that. That is not necessary. Okay, then I'm going to move over. There's no friction, so I'm going to move over to this guy. Okay, now this guy has, of course, the force of gravity. That's the force of gravity on the little m. And he has tension, but that's inside, so I don't have to worry about that tension. Recognize that in our ideal physics situation, that the tension here and the tension there are the same. And we may come to look at that in just a minute. But right now, recognize they're the same. That's not Newton's third law, by the way, but they are the same because we're simplifying the situation. All right? Here, we've got the force of gravity pulling down. And therefore, that's actually it. There's no normal force on this guy. And so, yeah, doesn't matter. So if we do the horizontal forces and the vertical forces, or in other words, the forces that cause the pulley to turn, that's going to be basically my x-axis. So this right here is my new x-axis. Anything that would cause the pulley to turn is that x-axis. Any other forces are going to be not along that axis, right? You'll notice here that this force of gravity and this normal force are going to cancel out, right? Those are going to be equal because my block isn't going to accelerate up or down as it sits on the table. And so it doesn't need to move. It's steady there. It's going to slide along this way. So there's no vertical acceleration or no motion perpendicular to the motion along the pulley, along the string, which is our x-axis here. And yeah, this is a little bit more complicated, but watch what it does to the mathematics, okay? If we do this, the only horizontal force, the only force causing rotation along the pulley is this guy right here. It's the force of gravity on the small mass. And so we can say that the sum of the forces is equal to mass times acceleration. And the only force along that axis is the force of gravity on the small mass. Now that needs to equal the mass of the whole thing. Okay, now both masses are going to be important because both of them are going to be accelerating as it moves that way. So we're going to go m plus m times the acceleration. And now we can solve for the acceleration. We do need this substitute for this, right? This is the force of gravity, which is mg. This is the small mass because that is the only mass that is receiving this gravitational force here. This one, remember, is balanced out by the normal force of the table on that block. All right? And so when we put it all together, we should get mg divided by vm plus m equals acceleration. And we solved for the acceleration. I know you can't see it. Don't tell me. There you go. So you've got mg over m plus m because we've divided by that to bring it over to the other side. All right? This is not divided by. That's just remembering. This is this. Same thing. Okay? Awesome. So that's our acceleration. The question did ask us to find acceleration and tension. And so that's the next job. The next thing we need to do is find the tension. Now, the tension is going to come from either one of these, right? Either one. You can't do it if you look at the whole system. Because if you look at the whole system, the tension's internal and it doesn't matter anymore. So what we need to do is draw a force diagram on one of the two objects, either the big one or the small one. It does not matter. All right? And so here we go. We're going to get rid of that. We'll do a force diagram on this guy right here since I got space. So the forces are the force of gravity on the small guy and then tension, right? And so we can do a sum of the forces on that. And so sum of the forces is tension up plus the force of gravity on the small mass, and that should equal the mass times the acceleration, which was mg over m plus small m. Now, a couple of things I did here, right? This is just only force diagram on small m. That's why here I'm using the small m, because that's the only one that matters. This is just a small m. We're not paying attention to anything else going on up here. Okay, so small mass times the acceleration. The acceleration is what we found over here. We found that in the first step, and we can put that in for the acceleration. The tension is what we're looking for, and now we're going to find this FGM, which we already know. It is mg. Now, when I put that in, we need to recognize that g needs to be a negative number. Generally speaking, we consider g to be 9.81 or 10 meters per second squared. We don't usually make g negative. You can put it in as negative, but we don't make it negative usually. Okay? Now, another thing that you'll notice is I'm not paying attention to the pull anymore. The pulley has nothing to do with this mass. Okay? This mass is affected by tension and gravity. It has nothing to do with the pulley. So this convention that we set earlier isn't important. All that's important is paying attention to the force diagram on this mass. Gravity is going to be downwards. Okay, so I am going to say this is minus mg to make sure that I have a negative number here. I'm going to add it to the other side. Okay, because remember here, same thing. Right here, same thing. I use a positive g here. That positive number is going to give me the acceleration. Okay, it was positive here because it was causing a positive rotation of my pulley. So over here, I'm going to get my final answer, which is that T is m times mg over m plus m plus mg. Okay, it should be an addition because it's going down this way. It is accelerating downwards. Okay, and so I should end up getting this number right here. Now, the one thing that I should mention is that I really should count this as negative because my acceleration is downward. I paid attention to all of that except for this last point right here. That acceleration should be downward. So this should be a negative mg over m plus m. Okay, always pay very close attention to your ups and downs. Okay, you could very easily count down as positive, in which case you should be subtracting this over here because that means this would be positive and you would subtract it over to the other side. Okay, so in the end, tension should be less than gravity because you're accelerating downwards. And so it should make sense that you're going to have one number positive and one number negative because the tension needs to be less. The tension needs to be greater if you're holding it up, but if I start lowering it down at an acceleration, the tension can be less because there's less strain. That's what tension is. There's less strain or less force on that string if I'm accelerating downwards, right? You could picture that if you hold up a mass and you just go down really quickly, the string will compress, right? There won't be any tension in the string at all if you go quickly enough. Okay, that's because of your acceleration downwards, and your acceleration downwards will then decrease the amount of tension in the string, which is why we end up getting this right here. Okay, that's the end of this question. I want to point out that you could do it this way, looking at the system. You can also look at individual pieces, right? We could have started off the same way that we started off in the last question, in example number 6. If we start off that way, remember to pay attention to the pluses and minuses, right? You still need to make sure that these T's are opposite directions because one of these T's is going to cause the pulley to rotate this way. The other one is going to go against that rotation. So one of those T's will end up being negative. Make sure your gravity has the same sign as whatever this is, right? You want to make sure that as you work through that you're being consistent as you connect pieces together. And that's one of the things that we're hoping to do as we work through more and more and more examples over the next little while. Okay, so there you go. We solved for acceleration, we solved for tension, and that is the end of this video.